Yesterday we talked about Dijkstra, which is the single source shortest path algorithm. So Dijkstra is the shortest path that we can use on weighted graph. So if we can use it on weighted graph, it can be also used on unweighted graph, right? This Dijkstra algorithm cannot be used on the graph which has this negative weight. Because it has this negative weight, then sometimes it does not give this optimal result. And because we assume that the graph contains only positive weight, so that's why it's fast. The time complexity is O E H plus V times log V. Log V comes from this extracting the minimum here. Extracting the minimum from the heap or priority queue. So with this G is the adjacent list, something like that. It's a data structure that we use to store the graph. We can use also the adjacent metric, right? In this case, is adjacent list, which gives the keys as the vertex, the values as the list of vertices it connects to. So for example, like this graph, 1 to 3, 1 to 2, the vertex 1 connects to 2 and 3, vertex 2 connects to 3 and 4, vertex 3 connects to 4 and 5, right? So this is unweighted. But if we going to use this same thing to store the weighted graph, instead of storing a single vertex, we can store a tuple with a weight. We also talk about breadth search for a long time, right? So breadth search is the shortest path algorithm we can use on the unweighted graph. Right? Let's take a look at this breadth search again, and you can find a lot of similarities between breadth search and Dijkstra, and also the the uniform cost search. We talk about the uniform cost search UCS in day 387, right? You probably forget, yeah? So breadth search, we use the queue, right? First in, first out. In Python, we use the DQ, right? Q equals DQ. So at the beginning, we push the source in. And of course, we need a hash set to remember the vertex we have visited. If we apply the breadth search on trees, we probably don't need the scene, the hash table, because the only way we can travel is from the parents to the kid. But in the unweighted graph, especially if it's a undirected graph, then we can travel between the vertex here and there, right? So we have to remember the vertex we have visited, so we don't go back, visiting it again. So why a queue means that why we have these elements in the queue, or why the queue is not empty, why the length queue bigger than 0, the length. So we take an element, v equals q dot pop left, right? And then we have to check if v in scene, then we continue. We have visited this before, we continue. Otherwise, we put it, if it's not visited, we put it in the scene table. Scene dot add the v, and then we travel the next vertex, right? We append the kit for x in g v, right? Then we append it back to the queue. So q dot append x, right? So here we forgot to check if we have to check here, right? So put it here. So if v equal e, then we find it, yeah? We return, we can return, if it's a unweighted graph, we can return the destination or return the path. We can have a variable storing the distance from the source. Return the distance. For example, if we push the distance along with the source, so here is 0x, right? So now we have this cost CV, right? Then we return C here, right? And then instead of append x, we can append the C plus 1x, right? Because when we visit the kids, the distance is incremented by 1, right? And then if we can't find it, we just return infinity or return -1, right? So look, this is breadth search. Do you see the difference and similarity between the breadth search and the Dijkstra here? Any difference? Breadth search on unweighted graph, Dijkstra on weighted graph. Right? Breadth search, the time complexity, OE plus V. Dijkstra, OE plus V log V. In the worst case, all the edges and vertex will be explored by breadth search. Right? And here, we're using the DQ. Here, we're using the heap. They both use the hash set to remember the vertex it's been visited. This is similar to append. Right? Look, this is quite similar. But here it checks, it update. Remember this Dijkstra, we update the estimate and we pick. Yeah, it has an extra step of updating the estimate. This is updating the estimate. If we find a shorter path, we update it. D, and here it uses the D. D stores the shortest path, shortest distance between the source to all other vertex. But here we don't have this data structure to store the shortest path from the source. Here we just find a single source, find the shortest distance between S and E. We just find this shortest distance between a pair of vertex. When we perform this Dijkstra, we have this D is complete. So Dijkstra is complete. BFS search here in this case particular is not complete. We talk about UCS. UCS, uniform cost search, is the variant of Dijkstra, right? It's a variant of Dijkstra. So we can change this bit slightly, then it will become a uniform cost search. You will be amazed at how easy it is to remember the uniform cost search. Right? So the idea is that every time we take the best out, we visit the best out instead of the first in, first out. We just change it to first in, best out, priority out. Okay? So okay, I'm just going to squeeze here. So uniform cost search. Okay, I'm going to use the green. So here, this is the same. So we change it to Q equals is heap 0s. Right, this is the same. Right, Q dot top left we use this. So this one we borrowed it here, and this one we just borrow this one. Okay, and that's it. So look, with the BFS search, we change 3 places and it becomes a uniform cost search. First of all, instead of using the Q, double-ended Q, first in, first out, we use the heap, which is a priority queue, first in, best out. Right here, we get it out. And then instead of a pen, we need to hit push. Right? And we don't have this step of updating the estimate. Right? This is uniform cost search, which is the variant of Dijkstra, and the time complexity is the same as Dijkstra. Right? It's not complete because as long as we find a destination, we just return the function. Right? Instead of finding all other shortest paths to all other vertex. To sum up, the uniform cost search in day 387, uniform cost search is a variant of Dijkstra. Both use the priority queue or heap, first in, best out. With the Dijkstra, it has this update estimate. It's a complete. It computes the shortest path from single source to all other vertex. For the uniform cost search, it's not complete. It's more similar to BFS search. The difference between the uniform cost search and BFS search is that the use of queue or priority queue. Right? All others are the same. Okay, that's it for today. Bye bye.